Welcome to the next problem solving session for the course Fundamentals of Food Process Engineering. In this week's session, we'll be solving problems related to week 9 syllabus, which majorly includes physical separation techniques with a focus on filtration. So, in this week, we'll be solving a lot of theory based questions as those are most recurring, and a few of them will be related to the filtration process as well as the Stokes equation, which we'll be discussing in this particular session. We'll start with the questions. Question 1. The capacity of a screen in separation is measured by the mass of the material that can be fed per dash to the dash of the screen. So A. Unit area to the rate of the feeding of screen. B. Unit screen size to unit volume. C. Unit time to unit area. And D. None of the above. So any clue what the capacity of a screen means? Yeah, the answer is C. So screen efficiency can be, so the effectiveness of a screen can be measured by two different techniques. One is the screen efficiency and the other one is known as the capacity. So the screen efficiency is a measure of how closely two materials A and B can be separated. That is how well you can separate A and B materials. And the other metric, which is the capacity of a screen, is measured by mass of the material that can be fed onto the screen per unit time per unit area. So it basically means that smaller the capacity, greater the effectiveness. So if you are able to load only a small amount of material, then you won't be overloading the screen, so your separation will also be good. But if you put too much mass of the material onto the screen, then the separation effectiveness will also reduce. So it's kind of inversely proportional. Smaller the capacity, greater the effectiveness. But you cannot have a screen always where you can put only small amounts of material. That will not be feasible for you. It will be time consuming if you have to do multiple rounds of screening process. So it is kind of a compromise between capacity and effectiveness. So you have to reach the optimum compensation between the capacity and effectiveness to have a feasible technique where you can also load higher amounts of material and also get an acceptable amount of separation. So the answer here is option C. Question 2. Which of the following is true for a disc ball centrifuge? A. The feed liquor is introduced at the base of the disc stack. The heavier liquor is collected at the bottom of the disc stack and light liquid at the top. B. The feed liquor is introduced at the base and both the liquids are separated and collected at the top. C. The feed liquor is introduced at the top. The heavier liquid is collected at the bottom and light at the top. And D. The feed liquor is introduced at the top and both the liquids are separated and collected at the top. So what is the stream's direction here? So in a disc bowl centrifuge, the feed liquor is introduced at the bottom of the base stack. That is, this is the disc bowl centrifuge where you send the feed through the bottom. It will fill through the entire volume of the centrifuge, and then once it starts rotating, the heavier particles, because it experiences a greater centrifugal force, will reach the walls of the centrifuge, whereas the lighter particles which relatively receive a relatively lesser amount of force will stay at the center. So once the centrifuge is done, you can collect the heavier liquid from the walls through this end and the lighter liquid from the center. So both the heavier and the lighter streams are collected from the top and the feed is let at the bottom. So the answer here is option B. Here is how the feed enters. It centrifuges. The heavier particles are thrown out to the walls of the centrifuge and you can collect it from there. The lighter particles will stay at the center and you can collect it from the center. So both the streams will come from the top, the feed will come through the bottom. So during the session, if there's any doubts, kindly let me know and either unmute yourself or post it in the in-call messages. So question 3, match the following. List 1, you have the different kinds of filters and parameters related to it, and list 2 is a force that matches these parameters. So A, you have cyclone separators, B, centrifugal filters, C, drag coefficient, and D, cake filters. And list 2, you have centrifugal force, pressure difference, centrifugal force plus gravity, and shape factor. So we'll go one by one. So what does A correspond to? The cyclone separators. So A corresponds to 3, B to 1, C to 4. Yeah. So the answer is option B here. So in a cyclone separator, it is majorly used for doing a solid gas separation where you have multiple particles in air and you need to separate these particles. So what happens is you send in the dirty air with a tangential velocity, and because of this tangential velocity, in a cyclone separator, the air will go in a cyclone-like format. That is, it will keep whirling around the cyclone in the cyclone separator, and at some point the heavier particles will have a centrifugal force, and because of this centrifugal force it will hit the walls of the separator, and once it hits the wall of the separator it falls down because of gravity. Whereas the lighter particles will not experience this much amount of centrifugal force, and hence it will be carried along with the air through the outlet. So that A corresponds to the third part. Now for the centrifugal filters, the centrifugal filters have use only the centrifugal force. So cyclone separators use both centrifugal force and gravity once the particles hit the walls, whereas centrifugal filters will use only the centrifugal force. Where you feed in your slurry, like how we discussed in the previous slide, you feed in the slurry through a certain direction and you centrifuge it, and the heavier particles will be stuck onto the walls because of the centrifugal force, and lighter particles will remain in the center, and based on that you can separate it out. And in the drag coefficient is highly dependent on the shape of the particle as well as the orientation in which it moves, and this drag coefficient is often used for calculating the terminal velocity of a particle inside a centrifuge. So, and then the driving force for cake filters is a pressure difference across the filter medium and the cake deposited on the filter medium. So it's basically like filtering out tea or anything, the basic examples that we see here. So driving force is the pressure between the outside of the filter to the pressure that you're giving on the filter. So that pressure will be the pressure difference across the cake that is being deposited as you keep filtering your slurry, and the pressure across the filter medium that has your membrane or any other particle that is any other material that is used for separating your materials. So the answer here is option B. Okay, question 4 again, match the following. This is also related to filtration based theory. So you have A, constant rate of filtration, B, intercept C of constant filtration, C, specific cake resistance, and D, kV in the constant rate filtration. And you have the formulas for each of these on the right hand side, the second column. So which of these correspond to which one? We'll go one by one. So the constant, you can in a filtration process you have two different things that you can keep constant. You can either keep the rate, that is dV by dt, as constant, or you can keep the pressure delta P as constant. So there are two different techniques in which you can do the filtration process. So in a constant rate of filtration where dV by dt is constant, the equation is given as dt by dV is equal to mu alpha Cs by A square into minus delta P into V plus mu by A delta P into Rm, where T is the time, V is the filtrate volume that you are taking out after the filtration. So V is the filtrate volume, alpha is the specific cake resistance. So as you filter, all your solid particles will get stuck on one side of the filter and it will form a cake. So that cake will also have some resistance to this mass flow rate across the to this flow across the membrane. So the cake also gives some certain resistance which is given by alpha. A is the filter area. Cs is the concentration of the suspended solids that need to be filtered. Delta P is the pressure difference across the media, across the entire process, that includes the cake as well as the filter medium. And Rm is the resistance due to the filter medium alone. So you have two different resistances here. One is because of the cake that is being deposited over the time during the filtration, and Rm is the resistance due to the filter medium, due to the membrane and so on. So this is the equation for constant rate of filtration. So in a constant rate of filtration, your dV by dt will be constant. Only your delta P will keep changing and your volume of filtrate that you are taking out will keep changing. Because over the time it will be more difficult to pass to keep your flow rate same. So as your cake gets getting deposited, it will be much more difficult to maintain that same flow rate, because now your slurry has to pass through the cake also and it has to pass through the medium, the filter medium also. So it gets more and more difficult. So the pressure across the filter medium also keeps changing, and obviously the amount of filtrate volume that you're collecting will also change with respect to time. So if I'm just rearranging here, I'm taking minus delta P to this side and I'm taking dV by dt to the RHS. So if I rearrange, so minus delta P here, minus delta P minus delta P is equal to mu ACS by A square dV by dt into volume plus mu dV by dt by A into Rm. I just took the delta P to the LHS and dt by dV to the RHS, so it became dV by dt. So if I now plot a graph between delta P and V, it will look pretty similar to this. You have all these are constant. Mu is constant, alpha is constant, provided you are looking at an incompressible cake. You have Cs constant and area constant, and dV by dt is also constant because you are looking at constant rate of filtration. So all these are constants, and let's say you take it as Kv. All these are also constant. The resistance due to medium is also constant for a particular kind of membrane that you are looking at. So Rm is also constant. So you have plus C here. And what I meant by incompressible cake is that sometimes the cake that is deposited on the filter medium can be compressed. That is, the properties will keep changing upon the resistance will keep changing depending upon the pressure. So if you have a compressible cake, the resistance will depend upon the pressure. If you have an incompressible cake, your alpha or your resistance will remain constant and will depend upon the slurry media that you are sending in and not on anything else. So here in this particular example, we are looking at an incompressible cake where alpha remains constant irrespective of the changes in delta P. That is our assumption here. So this represents that of a straight line where minus delta P is equal to Kv into V plus C, because everything else is constant, only the pressure and the volume of the filtrate keeps changing. So since this looks like a equation of a straight line, Kv or the slope can be given as mu alpha Cs dV by dt by A square, and the intercept can be taken as mu dV by dt by A into Rm. So your slope will have properties of the cake, your intercept will have properties of the filter media. Rm is due to the filter media. And what is alpha here? What do you mean by cake resistance is that it is derived from something known as a Karman-Kosny equation, which is described in the video lectures. So in the Karman-Kosny equation, you're looking at the specific cake resistance, because now it's very similar to that of a fluidized bed, or where you have particles and then your fluid flows between these particles. So similar to that, your cake will be a solid, and it will have pores in it, and your liquid will flow through these pores. So it is very similar to that of the fluidized bed, where again in that part also you have solids and your fluids will be flowing between these solid particles. So the specific cake resistance, the derivation for this is given in the video lecture. This cake resistance is derived from Karman-Kosny equation and is equal to K1 into 1 minus epsilon S0 by rho P into epsilon cube, where K1 is a constant, epsilon is the void volume between the solid particles, S0 is surface per volume ratio of the particles, and rho P is the density. So based on this, for a certain kind of material, as you can see, alpha remains constant if you are dealing with an incompressible cake. So that will answer the question that is being asked here. So the constant rate of filtration is given by this entire equation, where this part becomes the slope. If you put delta P here on the LHS and dt by dV on the RHS, this will be the slope. That is, Kv in the constant rate of filtration is contributed by the cake, which includes mu alpha Cs by A square dV by dt. The intercept is contributed by the filter medium, which is mu Rm by A dV by dt. And the specific cake resistance is derived from Karman-Kosny equation, which is K1 into 1 minus epsilon S0 square by rho P into epsilon cube. So the answer is option D here. So to answer this question, you basically need to just memorize this equation and convert it into that of a linear form, because only delta P and V changes. So if you convert it into an equation of a line, you can calculate what is the slope, which is the Kv, and the intercept, which is the C. So similar questions can be asked for constant pressure. So all those are given in the constant pressure will also have an equation like this, where you can convert it into an equation of a line and calculate the slope as well as the intercept. So that is already discussed in the video lectures. If you guys have any doubts, you can refer to the video lectures, or if there are further doubts, you can post it in the discussion forum as well. So question 5, select the incorrect statement about Stokes' law. Sedimentation separation follows the Stokes' law. Particles must be solid, smooth and spherical. Particles should not interfere with each other during the fall, and D, none of the above. Yeah, the answer is D. All of these statements are correct about Stokes' law. So the Stokes' law states that the force that retards a sphere moving through a viscous fluid is directly proportional to the velocity of the sphere, the radius of the sphere, and the viscosity of the fluid. So if you remember our very first problem solving sessions, where we discussed ball falling through a long cylinder filled with a liquid. Now, because of the drag force and the buoyancy force that will act opposite to the gravitational force, you will have Stokes' law coming in to account for the drag force. So in that technique, where we drop a ball through the liquid, we assume that the force that retards a sphere depends upon the velocity of the sphere, the radius of the sphere, as well as the viscosity of the fluid. And we'll be discussing Stokes' law time and again during this problem solving session. And in order to apply the Stokes' law, we have a few assumptions: that the particles are spherical in shape, that the fluid is flowing in a laminar flow. Okay, the fluid is flowing in a laminar flow. The composition is uniform, and also the fluid is also uniform and homogeneous. The particle surfaces are smooth and it does not interfere with each other. So if you have interference, so if you have interference between the particles, then the forces that you are counteracting, that is the gravitational force, the buoyancy, and the drag force, will now have an additional interference, and you cannot apply Stokes law in that. The answer here is option D. All the statements above are correct about Stokes law. Question 6. The filter press commonly used in oil mills is A continuous type pressure filter, B continuous type vacuum filter, C discontinuous type pressure filter, and D discontinuous type vacuum filter. Okay, so before we proceed, what is the difference between a continuous type and a discontinuous type? So a discontinuous type filter is basically where you have a lot of cake deposition happening, and after a certain point it will be very difficult to continue with the filtration process, because now your cake resistance will be very high and it will be very difficult to get the filtrate out. So you need to stop the process, clean out the cake, remove the cake, and then restart the process again. So in places where you have a lot of cake deposition happening and you cannot remove it, you introduce something known as a discontinuous type filter. And the filtration can happen due to multiple reasons. Either you can apply pressure, you can create a vacuum, or you have gravitational forces also coming into picture. So for oil mills, generally discontinuous type pressure filter are used, where your filtration happens in batch wise process, where you have to remove the cake and then restart the process again, and you apply pressure on the one side of the membrane so that the filtration process can happen. So discontinuous type pressure filters are what is preferred in oil mills, and the majority of the techniques that have been discussed, majority of the filters that have been discussed in the video lectures include the discontinuous type pressure filter, such as the shell and leaf filter, where you have a huge shell and you have multiple leaves inside. You will send the feed inside the leaf, or you can send it outside in the shell also. So basically you will send it in one direction, and after filtration you will collect the filtrate outside. You have shell and leaf filter. You have automatic belt filters, where you will send your slurry through a belt, it will filter out, you will get the filtrate collected down, and then later on you will have to scrape out the cake. And you have centrifugal filters also. So all these you cannot continue without scraping out the cake first. So at one point of time you need to stop the process, scrape out the cake, and then restart the process again. So that all these are discontinuous type pressure filters, and that is what is used in oil mills. So answer is option C here. So a more pictorial representation of all this is discussed in the video lectures for your reference. Question 7. Centrifugation can be used to A. Separate fat from water, B. Separate soil from seeds, C. Separate stone from rice, and D. All of the above. No, centrifugation is not used for all of the above processes. So during the centrifugation process, what is preferred is that at least you have one component that is liquid. You can either have a solid liquid mixture that you want to separate, or you can have a liquid liquid mixture with different densities that you want to separate. You, it's very difficult to separate a solid from a solid. So separating soil from seeds and stone from rice are very difficult in the centrifugation process. On the other hand, separating fat from water is easier because then you can, because of the density difference as well, you can collect differently. So oil, because of a lesser density, will probably be collected at the center and water will be thrown out. So you need at least one of the phase in liquid form for centrifugation to take place. For the rest of these, from stone, from rice and all, you have destoner instruments that we'll be discussing in the coming slides. Those can be used to separate solid solids with different specific gravities. In case of centrifugation, you require at least one to be of a liquid state. So it can be used to separate fat from water. Okay, so moving to question 8. If there is any question that needs to be repeated, please let me know. So which of the following is true for flotation? Flotation is used to separate heavy particles from the fluid. B. The application of flotation in the food industry is to separate small fat particles from water. C. The action of flotation doesn't depend on the surface forces. And D. All of the above. So which of these is true about flotation? So as the name suggests, things can float only if it is very light or if it is very fine. If you have a very heavy particle, it will not float, it will sink. So at that time you will use a process known as sedimentation, not flotation. So in flotation is used in case of settling the fine particles. So if you have a liquid if you have a liquid which has very fine particles that needs to be separated, you are putting in a flotation device which generally has an agitator. It will continuously mix it, and because of the surface forces, all your light particles will tend to accumulate at the top of the surface. So once the light particles accumulate at the top of the surface, you can just remove it from the surface, and the bottom will have the heavier liquid. So flotation is used in case of settling the fine particles, and it depends upon the relative tendency of air and water to adhere to the particle surface. So that is how it keeps the surface forces are what keeps the fine particles floating on the water. The action of flotation depends upon the surface forces. So the application of flotation in the food industry is to separate those light and small fat particles from water. If you are dealing with heavy particles and you want to separate them, then sedimentation is the go. If you want to separate lighter particles, then you have to use flotation, which depends upon the surface forces. So answer is option B, which is true. Okay, so moving to question 9, we'll have some small numerical based problems for the past 2 years. So we'll look at those small problems. A basket centrifuge of 0.5 meter diameter rotating with an RPM of 2000 develops a centrifugal constant of dash. Okay, anybody tell me what is a centrifugal constant? So we have the diameter given, we have the speed of the centrifuge basket given. So a centrifugal constant is given by v square, which is the velocity, by g gravitational constant, acceleration due to gravity, and into r, which is the radius of the centrifuge. So V square by GR is known as centrifugal constant. So it's a direct substitution here, but we have the speed of the centrifuge which is given in RPM. We need to convert that into velocity. So velocity can also be given as omega into R. So omega can also be given as 2 pi into n, where n is the rotation speed given in RPS. So 2 pi n gives the omega, where n is substituted in RPS, that is revolutions per second, into R will give me velocity. And again you have divided by G into R. So if I substitute the values, 2 pi into 2000 is given in RPM. I am converting it into RPS. So 2000 divided by 60 into R, which is 0.25 meters. You have the diameter given. So radius is 0.25 meters. So whole square divided by 9.81 into 0.25. So this gives me a centrifugal constant of 1117.9. Answer is option A. So V square, I am converting it into omega R. Omega R can also be given as 2 pi into this rotating speed of the centrifuge given in RPS. So hope this is clear. So throughout the session we'll be having these tiny numericals. So question 10. The centrifugal force acting radially in the cyclone can be written as WV square by GR, WV square by R, GV square by WR, and WV by GR, where V is the velocity, W is the weight, and R is the radius of the separator. So how do you find out the centrifugal force? So the centrifugal force can be given as m omega square R, and omega is also given as V by R. So centrifugal force can be given as mv square by R. If you substitute omega as V here, you have V square by R square, and R gets cancelled, so you have mv square by R as your centrifugal force. But here we don't have mass given, we have weight given. So weight is equal to mass into acceleration due to gravity, m into g. So if I substitute all this here, m as w by g and omega as v by r, so this is w by g and this is v square by r. So you have w v square by g r coming. So this is how your centrifugal force is given in a cyclone separator. Any doubts in this? Had the mass been given, that this will be the equation mv square by r. Since weight is given, weight is equal to mass into acceleration due to gravity. So you will have this coming in, weight by g into v square by r. The answer is option A here. Moving to question 11. In a cyclone separator, lighter particles take dash to settle. Are you guys able to see my screen? So if at any point if the PPT is not visible or it's going slow, please let me know. So in a cyclone separator, lighter particles take dash to settle. A shorter time, B longer time, C very short time, and D equal time. So if you remember the process of cyclone separator that we discussed in one of the previous questions, yeah, the answer is a longer time. So in a cyclone separator, you send in the dirty air that contains suspended particles in a tangential velocity, and it will come down the cyclone separator in a spherical manner. So the heavier particles will exhibit a higher, will experience a higher centrifugal force and will hit the walls and settle down quicker. Whereas the lighter particles will not experience that much of a centrifugal force, and hence it will take a much more longer time to settle. Sometimes it might not even be settled, and all the fine particles will be carried with the air that is taken out. So the settling velocity in a cyclone separator, if you want to look at from the formula point of view, the settling velocity in a cyclone separator is given as G into rho P minus rho into dP square by 18 mu V square, the tangential velocity square, by gr, where G is acceleration due to gravity, rho P is the density of the particle, rho is the density of the air or the fluid that is here, dP is the diameter of the particle, mu is the viscosity of the fluid, V tan is the tangential velocity at which you are sending in the particles, and your R is the radius of your cyclone separator. Sorry, the radius of your the radius of your cyclone separator. So the settling velocity, as you can see, is directly proportional to the square of the diameter. So if you're dealing with smaller particles, your dP will also be very less, and hence your terminal settling velocity will also be very less. If your settling velocity is less, then it will take a longer time to settle, and hence lighter particles do not settle and often pass out along with the outlet gas. So answer here is option B. Okay. Moving to question 12. Statement 1. A D-stoner separates the grain mass into two fractions based on the surface texture. And statement 2. The spiral separator separates the grains as per their specific gravity. So statement 1, is it true or false? So what is a D-stoner is that it will basically remove stones from either from rice or other products. So in a D-stoner, this is how it looks like. So you have your feed or your feed that contains these mixtures passed from the top, that will now enter a belt-like region where air is also being passed. So what happens is that because of the difference in the specific gravity between your stones and your product, you will have a separation. Apart from the air also, you will have constant vibration of the tray happening. Because of the constant vibration of the tray as well as air passing through, your product will be your product will be separated from this side, and your stones will go on the other direction. So the D-stoner separates the stones from the products on the basis of difference in specific gravity. So the stones having a higher specific gravity than the product do not move upon fluidization with the air. So when you pass in air from the bottom, you will have a fluidization like process happening, where your lighter particles will behave like a fluid and pass through easily, whereas your heavier particles will remain almost stationary. But now since you are vibrating the tray, all those heavier particles will now move to the other side. So the tray is vibrated in such a manner that the heavier particles or the stones separate at one end and the product falls at the other end. So statement 1 is false. It is not based on the surface texture, it is based on the specific gravity of the particles. So statements 2 is also false because you're looking at a spiral separator. This is how a spiral separator looks like, where you pass the feed on the top, and now all your particles will roll down slowly till the bottom. So what happens is that if you have a round material, that will be able to roll much easier than an irregular shaped material. So if a round material starts rolling even faster and faster as it goes down, at some point of time, it will reach enough velocity to come out of the spiral. So when you're going very fast, you will be able to come out of the spiral. Whereas your irregular particles, which will not have that high of velocity, will continue to pass through the insides of the spiral and you will collect it at the bottom. Whereas your round materials which attain enough velocity to come out will be collected on the sides. So a spiral separator are made up of inner spiral flights and outer spiral flights. So you have something known as an inner spiral flight here and an outer spiral flight here. So you have inner flights and outer flights. The round materials roll down faster than the materials with the irregular shape, and the orbit of the round materials will keep on increasing as the velocity also increases. The radius in which it goes out in a spiral manner, that is the orbit, will also keep increasing till it falls off from the inner flight to the outer flight, hence resulting in separation. So here the roundness of the material such as seeds will dictate the separation. So statement 2 is also false. It does not depend upon the specific gravity. It depends upon the shape of the particle. So both the statements are false. The D-stoner separates based on the specific gravity, and the spiral separator separates based on the surface shape or the roundedness of the particles. I hope this is clear. Any doubts in this? Okay, so question 13. Statement 1. Clarifying filters are used when particles to be removed are smaller than the filter pores. And statement 2. The cross flow filtration involves a slurry passed perpendicular to the filter medium. So which of these are true or false? So we'll start with statement 1. So what a clarifying filter is that you have a filter medium with all these pores. Now these pores will not be as straight as shown in the figure here. It will be a long tortuous pores. So when you're passing slurry through a clarifying filter, all your particles will actually be smaller than those of the pores. So it will easily go inside the filter medium. So all the particles will go inside the filter medium, but because of these long tortuous pores, these particles at some point will get stuck inside the filter medium. And what you receive at the other end will be a clarified filtrate. So that is what happens in a clarifying filter. The particles will enter the filter medium, but it will get stuck somewhere during these pores. And what you get out is a clarified medium. So hence statement 1 is true. Yes, the particles are smaller than the filter pores. That is when it is able to enter inside and get stuck. And statement 2, in a cross flow filtration, the slurry is not passed perpendicular to the medium. The slurry is passed parallel to the surface of the filter. So if this is your filter membrane, you will not pass the slurry in the perpendicular direction as you see here. You will pass it in a direction parallel to this. So because of this, and you will pass it at a very high velocity. And because it is passed at a high velocity and it is passed in a direction parallel to the membrane, you will get the filter being collected here, the filtrate being collected here. But what you need to notice is that there will not be any cake deposition here, or there will be very minimal cake deposition because you're continuously passing it at a very high velocity. So nothing will get stuck on here. Everything will get passed to the other direction. Whereas if you had passed your slurry in a direction perpendicular to it, you will have small particles being deposited here over time, and you will have something known as a cake deposition. So those are known as cake filters. So you have three types of filters. You have cake filters where you're passing it in a perpendicular direction, but in a cake filter your particles will be bigger than that of the filter size. So everything will get stuck on top. So that is the cake filter, where you'll have everything stuck on the top and you have the deposition of a cake. Whereas in case of a clarifying filter, that will again be in a direction perpendicular, but then the particle size will be small so that it gets stuck inside the filter medium. And in case of cross flow filters, you will pass the velocity, you will pass the slurry at a direction that is parallel to the membrane, so you will not have any cake buildup at all. So the flow is tangential to the filter medium. So answer here is option C. The first statement is true, the second statement is false. Hope this is clear. The three types of filters have been extensively discussed in the video lectures as well, if you guys want to go back and read about it. Moving to question 14. For a cyclone separator of 0.3 meter in diameter with a tangential velocity of 15 meter per second, calculate the separation factor of the cyclone separator. See, how do you proceed with this? What is the separation factor in the cyclone separator? So in a cyclone separator, the separation factor is defined as the ratio of the centrifugal force to the gravitational force. So if you remember, in a cyclone separator, you will have your particles coming down in a spiral manner, where the particles will experience a centrifugal force, and once it hits the wall, it will experience a gravitational force and everything will come down. So in a cyclone separator, you have both the effects of centrifugal force as well as gravitational force. So the ratio of these two forces is called as the separation factor. So a separation factor is Fc, which is mv square by r, which we discussed in the previous one of the slides. Mv square by r is given as a centrifugal force, and gravitational force is m into g. So m gets cancelled. You have the velocity given here as v, and you have the radius also given. So I'm just substituting the values here. Mm gets cancelled. You have separation factor as s equal to v square by r into g. So v, I am substituting it as 15 meter per second. R here, diameter is given as 0.3 meters. So I am substituting the radius as 0.15 meters. And the acceleration due to gravity as 9.81 meter per second square. So if I calculate this, I get a separation factor of 153. Answer here is option A. Okay, now moving to question 15. The cut diameter in a screen process and a cyclone separator is given as A, the diameter at which 90% of the particles can be removed, B, the diameter at which the particles cannot be separated, C, the diameter at which the particle size is same as the width of the screen opening for a screen process, and for a cyclone separator it is the diameter at which 50% of the particles are removed, and D, minimum diameter at which separation is possible. So if you have gone through the video lectures, you will time again come across a term known as DTC, which is the cut diameter. And for each process you will have something known as the cut diameter, where you have a different definition for each of these processes. So what is the answer for this So in case of a screening process, a cut point diameter or a DCP, as I told, is the diameter of the particle which has the same width as the screen opening. So if you have multiple particles and you're passing it through a sieve, the sieve will have sieve or screen will have tiny openings or pores. So the diameter of the pore, when it becomes equal to the diameter of the largest particle that you're sieving, that is known as the cut point diameter. So the screen opening is equal to that of the particle size. That is known as the cut point diameter. So that is the definition for a screening process. But for a cyclone separator also you have known as a cut point diameter, but the definition is different. For a cyclone separator, the cut point diameter or the cutoff diameter is the diameter at which 50% of the particles are removed. That is, your efficiency is 50%. You collect 50% at the bottom and 50% goes out with the exhaust gases. So that is the cutoff diameter for a cyclone separator. So as you can see here, the same definition, it has a different meaning for different kinds of physical separation techniques that we are looking at. For a screening process, it is the diameter of the opening, diameter of the particle which is the same width as that of the screen opening. And for a cyclone separator, it is the diameter of the particle that will undergo 50% efficiency in that particular cyclone separator. So answer here is option C. Moving to question 16. A basket centrifuge of 0.6 meter in diameter and 0.4 meter high contains 50 kg of water. Calculate the pressure at the wall if the centrifuge rotates at 6000 rpm. So this is the centrifuge that we are dealing with. Let's say capital R is 0.3 meters. The diameter is 0.6. Your R is 0.3 meters and it is 0.4 meter high that contains 50 kgs of water. If the centrifuge is rotating at 6000 rpm, we need to calculate the pressure that is experienced in this region, that is the wall. Any clue how to proceed with it? So since in a centrifuge we are dealing with centrifugal forces mainly, the centrifugal force can be given as m omega square r, or you can also give it as mv square by r. So in this case, Fc is equal to m omega square r. I am taking a differential. So for a small region, let's say a small region in the centrifuge liquid, which is of a mass dm, it experiences a centrifugal force of dFc. So dFc is equal to dm into omega square r. And that small strip that has a mass of dm, that can be calculated as rho into v. That is, density into volume can give you mass. So volume can also be given as area into dr. Area is this particular region and dr is this small thickness. So volume can be given as this entire area into dr, and that into density will give me the the mass associated with this small strip of liquid, small region of liquid. And we know that to calculate the pressure is equal to force by area. So the small pressure, differential pressure that this a region is experiencing is equal to the small the differential, that is the dFc, the centrifugal force that it is experiencing, divided by area, which is equal to rho omega square r into dr. So here I am substituting the mass, the dm, as rho a into dr. And then if I divide it by area, that is, if I am substituting dm here, dFc will give me rho a dr into omega square r. So now I am bringing a to the LHS, which will give me dFc by a, that is equal to rho omega square r by dr, and force by area can be given as dp. So now if I'm integrating this from 0 to P here on the LHS, and in the RHS I'm taking from all the way from Ri to capital R. So when you're centrifuging a liquid, there will be a small region at the center where there will be no liquid present, because everything is thrown towards the walls of the centrifuge. So your liquid will actually be only present from Ri to capital R. The rest of the region will actually be void. This Ri will be very less, but still we have to consider for it. So we are integrating, since the liquid is present only from Ri to capital R, we'll be integrating from Ri to capital R. So if you integrate R dr, that will give you R square by 2, and when you put in the limits Ri and capital R, this is the formula that you get. P is equal to P experience at the walls is equal to rho omega square by 2 into capital R square by Ri square, where rho is the density of the liquid that you are centrifuging. Omega square represents the speed at which you are rotating the centrifuge, and you have capital R, which is the total radius of the Bast centrifuge, and Ri is this particular region, the radius at which your liquid level starts. Now in an actual scenario, you have the density of the density of the water is 1000 kg per meter cube. You have the speed at which the centrifuge rotates, but you have the capital R as well, but you do not know what is small r. So in order to calculate that, since liquid is present only between Ri and R, the total volume of that particular region, so this particular region volume can be given as pi r square h, because it's basically a cylinder. The entire Bast centrifuge is a cylinder, and you have a hollow cylinder right now, where the center has nothing and the annular region has your liquid because of the centrifugal force. So since the liquid is present only between Ri and capital R in the cylindrical tank, the volume can be given as pi r square minus Ri square into h. Is this part clear? Because from the center to the Ri you do not have any liquid at all. The entire volume is present on the annular region between Ri and capital R. So that will give me the volume of the liquid present. And volume can always be given as mass by density. Is there any doubt so far? Why we consider this? Because it is difficult to measure Ri. You need to employ such methods to calculate what is Ri. So we have what is mass given as 50 kg. 50 kg of water is what you are centrifuging. So mass is given 50. You know the density of water, which is 1000 kg per meter cube. We have to calculate what is R square minus Ri square. The height of the tank is given as 0.4 meters in the question. So from there we can calculate what is R square minus Ri square, which comes out to be 0.0398 meters square. You need not even calculate what is Ri, you can just directly substitute this entire thing in the equation, in the previous equation that we were seeing. So R square minus Ri square is coming out to be 0.0398 meters square. So in the previous slide we calculated the pressure at the wall given as rho omega square by 2 into R square minus Ri square. So omega is omega is not in RPM. Omega is given as 2 pi into n, as we discussed in one of the previous questions. Omega can be given as 2 pi into n, where n is the speed of the centrifuge that is rotating in RPS. So omega can be given as 2 pi n, where n is given in revolutions per second. In the question we have revolutions per minute, so we are converting it into revolutions per second. So we will go one by one. Rho, I am substituting it as 1000 kg per meter cube. Omega is 2 pi into n, and n I am substituting as 6000 rpm divided by 60 to convert it into revolutions per second. So this whole square will give me omega square. And r square minus ra square is what we are deriving from here. 0.0398. Upon this, you get a pressure of 7850 kilopascals. Answer is option B here. So just to give a small recap, upon centrifuging, your liquid will be thrown out towards the walls. So the center will not have much liquid at all. So your liquid is present only from Ri to capital R. So in order to calculate the pressure at the walls, you first calculate what is the centrifugal force for a small region of the liquid and then integrate it from Ri to capital R. This will give us the pressure at the walls. We have all the parameters here. We do not know what is R square minus Ra square. So we resort, but we know what is the mass of the water given. So the entire mass is in the annular region of this cylinder. So we calculate the volume of the cylinder, which is given as pi r square minus Ra square into h. The volume can also be given as mass by density. You substitute the mass and density and you can know what the height of the tank is, which is given in the question. From there you can find out what is r square minus Ra square, which is substituted back inside the pressure equation. And omega is not given in RPM, it is actually radians per second. So you convert this into 2 pi into n, where n is given in revolutions per second. From there you can get the pressure. So always when you are looking at omega, please do not substitute in RPM, convert it into 2 pi n and then substitute the n value in RPS. Is there any doubt on this question? Anything that needs to be repeated? Question 17. A separation process requires the centrifugation of a product at 10,000 G. So this is the speed of the centrifugation. 10,000 G is the speed of the centrifugation. A centrifuge with an effective bowl diameter of 24 centimeter is available. So what should be the speed of the centrifuge to meet the specification? So we have it in 10,000 G, which is in RCF. But we need to find out the value of the speed in RPM. So how do you convert RCF to RPM? So this is basically the centrifugal acceleration that is given 10,000 into G. The centrifugal acceleration can also be given as omega square r. Now if you multiply that into mass, you will get centrifugal force. So the rest of this thing is centrifugal acceleration. If you remember, the centrifugal force is m omega square into r, where the acceleration is given by omega square into r. Okay, so centrifugal acceleration is given as 10,000 G. So I am substituting the value as 10,000 into 9.81, where G is the acceleration due to gravity. And again, omega square you have to give it as 2 pi into n, where n is given in RPS. So 2 pi n square into radius of the bowl, which is 12 centimeter or 0.12 centimeter. Diameter is given, we convert it into radius, which is 12 centimeter. So I am substituting it in meters as 0.12. So acceleration is given, everything else is given, you need to find out n. But the value of n you will get will be in revolutions per second. The question is asked in revolutions per minute, so we will convert it into revolutions per minute later. So from this we get 10,000 into 9.81 divided by 0.12 by 4 pi square. And then you take a root of it, you will get n as 143.9 RPS. Now if you multiply that into 60, you will get it in RPM, which is 8,634 revolutions per minute. The answer is option D. So this is how you convert RCF into RPM. Okay. So moving on to the last question of the session. A sedimentation tank 1.6 meter wide is fed with a slurry containing starch particles of 30 micrometer diameter and a density of 1220 kg per meter cube. What is the length of the settling tank required to treat 4300 liters of slurry per hour? So we're looking at sedimentation process here. So how do you calculate the settling velocity first? From settling velocity we can calculate what is the length. So when you're dealing with settling velocity, again when we have particles, starch particles, let's assume that to be spherical with of 30 micrometer diameter. So your starch particles, when you're keeping it stationary, it will experience three different forces. One will be the gravitational force, the other one will be the buoyancy force, and other one will be the drag force. So when you balance out these three forces, that is Fg minus Fb minus Fd equal to 0, and then you simplify the equation further, this is the equation of the settling velocity that you get. The equation has been derived in the video lectures and in previous problem solving sessions as well. So you can go through those to learn about the derivation. So the settling velocity of a particle can be given as rho p minus rho f into g into dp square by 18 mu. So rho p is the density of the particle, rho f is the density of the fluid outside, g is the acceleration due to gravity, dp is the density of the diameter of the particle, and mu is the viscosity of the fluid. So this will give us the settling velocity. But velocity can also be written as flow rate by area, which is Q by A. So we know what is the density of the particle given as 1220 kg per meter cube. We know the density of water as 1000 kg per meter cube. G is given, dP is given, and we still do not know what is the viscosity of the water is something that we know. So if I am just substituting the values here, it is given, the flow rate is given as 4300 liter per hour. So you need to convert it into per second basis. So you have 4.3 divided by 3600, and area we still don't know. We have rho p as 1220 kg per meter cube, rho f as 1000 kg per meter cube, g is 9.81 meter per second square, diameter of the particle is in micrometer, we are converting it into meters. So 30 into 10 power minus 6 the whole square, and you have 18 into viscosity of the water is 0.001 Pascal second. So density of the water and viscosity of the water might not be given in the question, but since it's very common, you need to know these values. So if I am substituting this, I get an area of 11.08 meters square. So I converted liters to meters, meter cube, and then per hour to seconds. So everything is SI units here. Converting diameter into meters, which is micrometers given in meters, and mu is also in Pascal second. So if all of these in SI units, the area that I am getting is 11.08 meters square. So area you have, you know one of the dimensions of the A tank. Area here we are talking about is the area of the tank. So area of the tank can be given as this cross-sectional area, which is length into breadth. So the breadth is given as 1.6 meters. We need to calculate what is the length of the settling tank. So length into breadth gives the area. We already know the breadth is 1.6 meters. From there you can calculate the length to be 6.925 meters. Answer is option D. So moment something known as settling, you're dealing with settling concept, you can apply the settling velocity equation to calculate the further parameters that are asked in the question. So with this we wind up today's session. So in majority of these you will have theory based questions that are very related to either the cyclone separator or the filtration process, and time and again you will have the settling velocity also coming into question. Settling velocity and centrifugal force coming into the problems. So these will be the common problems that are being asked in the assignments as well for the past 2 years. So if there's any other doubts during this problem solving session, kindly let me know. We'll take this up.